Hi everyone, let's start our last lecture in this series. So my congratulations to those who survived till the very last lecture. As usual, I start with reminding some facts that we discussed previously, and there are just two such facts. So first, we discussed quantum Hall effect, and it's a situation which is two-dimensional electron gas. It's a unitary symmetry class, no symmetries, class A. And we found that to describe this system, we need to add a Prussian term to the sigma model, Prussian term, which takes any integer values depending on how many Landau levels are filled. So Prussian term, also called, it's the same, it's equivalent, also called theta term, takes values from the group of integer numbers. Another example that we have seen is the quantum spin Hall effect, SHE, quantum spin Hall effect. It is also two-dimensional. It is from symplectic class, so it's time reversal symmetric with strong spin-orbit coupling. And in order to describe it within the sigma model, we actually studied the edge theory, not the bulk theory, but the edge. And we found a 1D theta term, one-dimensional theta term. It lives on the edge, not in the bulk. One-dimensional theta term that takes values from the group Z2. So it takes just two values, either 0 or 1, even or odd. It counts how many edge modes we have there. In this class, we have always counter-propagating edge modes, spin-polarized counter-propagating, and the only distinction is whether this number is even or odd. If it's even, it means they will all be localized, and this is just the usual two-dimensional metal. Everything is localized. If the number is odd, it means that something remains delocalized in the edge. So that's just the information we discussed in previous lectures, and for today's lecture we will generalize these things to all possible classes and to all possible situations. And in order to do this, we will first discuss the topic which we already touched a little bit earlier. We will discuss what is the notion of homotopy. This is a very complicated mathematical topic. I'm not an expert in mathematics, so I will just show you some facts, some simple examples without any proper definitions or proofs, but I will try just to create some feeling of what this thing is. So imagine we have a sigma model, we have a Q matrix which lives in a certain manifold M, and this manifold takes one of 10 possible structures corresponding to 10 classes. So whenever we have this Q matrix which depends on the point in real space, this Q matrix actually realizes a map. It maps a point from real space into this manifold M. And real space, for some stupid reason, is a sphere. Yeah, this is real space. And our point R belongs to this real space. But we always assume that somewhere at infinity, this Q matrix takes a single value, so this infinitely distant point is, this infinity is a single point, so no matter which direction you go to infinity, you end up at the same point. That makes our real space a sphere, and if it's a d-dimensional space, it's a d-dimensional sphere. So for 2D, it's just a usual two-dimensional sphere. For 1D, it's a circle, which means that going far to the right or far to the left, we end up at the same point. 3D means three-dimensional sphere, so on. M is the manifold of the sigma model, and this is a continuous map. It's a continuous map, simply because Q matrix should continuously change in space. Otherwise, we cannot take gradients of it. And at this point, some mathematicians come up and say that such continuous maps from a sphere into some topological space can be classified according to their homotopy. What does it mean? If we have two different continuous maps, so if we have Q1 of R and Q2 of R, two configurations of the Q matrix, which map from the same real space to the same manifold, but they're different. I mean, they're two different functions. We can define the notion of equivalence. So we call two such maps equivalent. They are equivalent or topologically equivalent if we can create a new map which depends on R and on extra parameter t. This extra parameter t changes from 0 to 1 in some finite interval. And it is such that it is equals to Q1 of R for t equals 0, and it equals to Q2 of R for t equals 1. And it should also be continuous. Continuous with respect to all the arguments, both to R and to T. So we have once again, we have two maps, two functions Q. If we can continuously deform one of them such that it becomes the second of them, these two are equivalent. Yeah?
We define difference between two Qs at two different times.
I did not get the question.
To understand that something is continuous, we should define distance.
Okay, mathematical definition as rigorous as I can. Two maps Q1 of R and Q2 of R are equivalent if there exists a function Q of R, comma t, which is continuous in all variables, such that for t equals 0 it takes the value Q1, and for t equals 1 it takes the value Q2.
Actually, the question was what is continuous in that sense?
In which sense? Again, continuous is like usually in mathematics, you slightly change the argument, the function also changes slightly. What's the question?
Doesn't matter.
No, seriously, I mean...
If you are changing t slightly, distance between two Qs in two different points of time will be also
small.
Limits to 0.
Yeah.
But what is the distance? How to define distance?
Ah, the distance is defined in the manifold.
Okay.
So this is a continuous, it's a topological space, it's a continuous manifold. Actually, we have metric there. So just an example. Imagine you have, imagine this board, this thing is our space M, and we map S1, one-dimensional sphere here. This is a loop. Yeah, this is a map from S1 onto the board. This is another map from S1 into the board. Are they equivalent? The answer is yes, because I can define a new function which for t equals 0 takes this loop, for t equals 1 takes this loop, and for all t's between 0 and 1, it continuously changes. It shrinks this loop slightly until it reaches the form of the inner loop.
Yeah, I'm just asking what is the distance between two loops?
No, it's not. There is no distance between loops. There is distance between points on the board. Q of R and T is a function that takes values in the board.
Okay.
Okay, R squared plus T squared
Okay,
square
okay,
root,
okay.
if you like. If that was your question, I still don't
Yeah,
understand.
that's
Okay, yeah. So two maps are equivalent if we can continuously deform one into the other, which means that all possible maps from this to that can be separated into classes of equivalent maps. These classes are called homotopy classes. And in principle, on this board, there is only one homotopy class with respect to S1, because any loop that I draw here, I can continuously shrink to a single point somewhere. And if I have two such loops, I can take one, shrink it to this point, and then undo this and make the second loop. So there is a continuous transformation between any two loops on this board, so it's only one homotopy class. But if I make a hole in this board, then so this is a hole, this is the place which is unavailable. There is nothing here, it's a void. Then I can have a loop like this, or I can have a loop like this. And these two loops are not topologically equivalent because I cannot continuously change this to that one without crossing the void, and void is not the part of my space, so I cannot map there. So there are two examples of non-equivalent loops, and actually there is a third loop which is not equivalent to any of these, and it's a loop that goes twice around the void. It also cannot be mapped to this or to that. So in this case, if I have a board with a hole, there are many homotopy classes, and all these homotopy classes are labeled by an integer number, which is just how many times my loop goes around this hole. It can also go in the opposite direction, so it can be a negative integer. So, example. We will have many examples, actually. Pi 1 of S1 equals Z. We already discussed this before. So if this board with a hole actually is topologically equivalent to just a circle. So mapping a circle, one-dimensional sphere, into one-dimensional sphere allows for any integer number that counts the winding. It's the winding number. This integer Z. Another example, which we also discussed before, pi 2 of S2. This is when I forgot to say, that these homotopy classes, these different homotopy classes, form a group which is called homotopy group, and which has a notation. Homotopy group is denoted pi with an index d of m. D is the dimension of the sphere, and m is the manifold to which we map. So pi 1 of S1 means we map one-dimensional sphere, just a loop, a circle, into another one-dimensional sphere.
How to define the operation on this group?
I will tell it a bit later. Yeah, so pi 2 to S2, we also discussed this. It is also Z. We have any integer number of these different homotopies, and we called it the degree of the map. Degree of the map. yeah, whether the sphere is covered 0 times, once, twice, 3 times. It's the same as winding, but for two-dimensional spheres. And actually, there is a whole statement about this generalization. Pi d of SD always equals Z. It's simple, yeah, it's just particular cases of this general statement. There is also another general statement, which is very easy. Pi with an index. Oh, let me write it as a single formula. Pi I of S D. There are 3 cases. Case number 1, if I is smaller than D. Imagine we are trying to map one-dimensional sphere, a loop, onto a two-dimensional sphere, onto a usual sphere. How many homotopy classes do we have?
Just trivial.
Just trivial, yeah. Any loop on the surface of a sphere can be shrunk to a single point. So all loops are topologically equivalent. So, and this is actually correct whenever I is less than D. When you map a smaller sphere onto a larger sphere, you always get it, I will call it 0, which actually means a group of a single element, a trivial group. Then there is a case when I equals D, and this is always the group of integer numbers. So when you map a sphere onto a similar sphere of the same dimension, you always have a degree of this map to be an integer number, and maps with different degrees cannot be transformed one into the other. And finally, there is an interesting case I larger than D, when you map a larger sphere onto a smaller sphere. And this is the most interesting. The answer is unknown. I mean, this problem is solved for various values of I and D, but there is no general formula. This is a very complicated mathematical problem which is unsolved until now, and the simplest example is when you map the 3-dimensional sphere onto the 2-dimensional sphere, 3 on 2. If you map 2 on 1, it's trivial, it's just nothing. If you map 3 on 2, it's called Hopf vibration. The answer is Z, but to prove it, it's not easy even to visualize, but this is just the simplest example. When you map 10-dimensional sphere onto the 5-dimensional sphere, the group can be really complicated. And this thing is computed for particular values of I and D, but as I said,
Do you have an example of different answer from 0 to Z?
there are, but they're even more complicated. So in some cases you can have Z12 here, like 12 different classes. But I forgot for which values of I and D. But you will not, it's not possible to imagine. It's really multi-dimensional space into multi-dimensional space. It's something I cannot simply draw. But we will not need this. It's just an example. Okay, let's consider some other spaces other than spheres. There are other spaces. There is such a thing which is called projective, real projective space. R, real projective space N. How many of you know what this means? It's almost like a sphere. Real projective space N is when you take the n-dimensional sphere and then you say that opposite points, which are opposite to each other, are actually identical.
So it's like half of the sphere.
It's half of the sphere, but with a certain boundary conditions. You can, yeah, so Actually, it's like a sphere is the space of unit vectors. You take a unit vector in 3 dimensions, you rotate it, and you get a usual sphere, or in any dimension. And projective sphere or real projective space is when you take not a unit vector, but you take just a straight line, which is infinite in both directions, and then you rotate it in all possible ways. So if you flip it, it's the same line, right? There is no distinction. So all possible lines going through 0 form the real projective space. All lines going through 0 in n+1 dimensional space form a real projective n-dimensional space. So, a simple question: what is pi1 of RP2? RP2 is just like a usual sphere, usual two-dimensional sphere, but the opposite points are identified. Opposite points actually represent the same point of this space. So you can always draw it. This is a usual sphere, and this point is actually the same as this point, and this point is the same as this point, and so on. So, if I draw a loop here, this is my loop. Can you really shrink it to a single point continuously? The answer is yes, it's easy. Yeah, you just take it and shrink. However, on the same real projective space 2, the same sphere, there is another type of loop which goes like this. It starts from this point and ends at this point. And these 2 points are actually equivalent. It's the same point in the genesis. So this loop is also closed. It goes back to the same point where it started. But this loop cannot be contracted to a single point, because if you change it continuously, this thing, it can only go around the sphere, but cannot really collapse to a single point. So if this is something unintentional. So this is actually Z2. This is the first example, which is not 0 and not Z. Real projective sphere has loops that are either equivalent to a single point or that have one jump like this. Yeah?
I just wanted to ask, like 15 minutes ago, this question. I felt a little bit shy, but I understand if I don't ask, it will be worse. So we started with quantum transport, and now we're doing pure mathematics. So how
Right.
this is connected?
This is connected in the title of this course. It's called Quantum Transport and Topology. So that was quantum transport, and now this is topology.
Should I guess some physical effects from
Yes.
They will be later.
Yeah, they will be later today, because it's the last lecture, so there will be nothing after today.
Sorry, pi always means when the manifold M is a sphere
No,
with I dimensions, or
no, not M. This one from which we map is a sphere with d dimensions, and this is the index of pi.
okay.
Pi d
Oh, okay.
corresponds
And
to
the
this.
M is what is written.
And M is what is written in brackets. It can be any topological space.
Okay.
No restrictions at all. So this is the first and simplest example of Z2. Now now this next example is very famous. If you take any book on Lie algebras, this will be written on the first page, maybe on the second page. Group SO3. What is pi1 of this group? SO3 are all 3 by 3 matrices which are orthogonal and have determinant 1. Special orthogonal group of matrices of size 3. These matrices of size 3 are the rotations in real space. If you take anything and you rotate it, you can describe this rotation by an orthogonal matrix. And if it's a continuous rotation, it will have determinant 1. So determinant -1 means inversion. So if we just rotate but do not invert the space, it's SO3. So how many rotations do we have in our three-dimensional space? Any rotation in three-dimensional space can be described by the axis of rotation and by the angle of rotation. So there is a direction n, which is a unit vector in 3 dimensions, and the angle theta, the angle how much we rotate around this axis. And actually, n is any unit vector, and theta, let me move it a little bit, and theta is the angle of rotation, which should be between 0 and pi. If you have a direction up and you rotate pi, means 180 degrees, there is no need to rotate more than 180 degrees, because you can say that let's flip our axis pointed down, then we rotate in the opposite direction, and it's less than pi. So whenever you have a rotation on the angle more than pi, it means you can change the axis and make this rotation with the angle less than pi. Yeah, so actually we can visualize all points of this SO3 group as a ball. It's a ball, a solid ball with its whole interior filled with points, with a radius equals pi. So when theta equals 0, we are in the middle of this ball, and this is a trivial transformation. We do not rotate anything, so it also doesn't matter which direction of n we have. That's why they are very nicely meet at the center. And if we have a direction, we better, and with different angles, we can have longer, 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 up to pi, and then this ball represents all possible rotations. And now an interesting question. What is this manifold? It's a three-dimensional manifold.
RP2.
This is actually RP3. It's three-dimensional. This is RP2. And you have only the surface of the sphere, and you identify opposite points. Now, why is it RP3? Yeah, actually, it's not RP3. I'm sorry. It's just a three-dimensional ball. But if you take this point on the surface, if you take this point on the surface, it represents a rotation along the certain vector by the angle pi. And if you take the opposite point on the surface, rotation along the opposite vector by the angle pi, they are actually the same rotation. I mean, it doesn't matter if you rotate by pi along this direction or that direction, you will end up in the same position. That's why we have all these points inside the ball are different, but the opposite points only on the surface are equivalent. This is a topological space. I cannot say more about this. It's a three-dimensional space, which is represented by this ball, such that points on its surface are opposite points on its surface are identified. So what is pi 1? If I now draw a loop inside this ball, now it's not on the surface, it can go inside as well. Can it be contracted to a single point continuously? Yes. What if I draw this loop, which goes from here to here? Again, on the surface, they are equivalent points. Can it be contracted? No. So actually the answer is also Z2. It's very similar to what was here on the sphere, but now we also filled all the interior of the sphere. It's like RP2, but filled inside. It's the same story. And there is another question. What is the group SU2? SU2 is the unitary matrix 2 by 2 with determinant 1. How can we visualize an SU2 matrix? It's very easy. SU2 matrix, any SU2 matrix can be written as exponent of I n sigma theta. It's an exponent of anti-Hermitian matrix. And anti-Hermitian matrix is I times Hermitian matrix, and Hermitian matrix can be expanded in Pauli matrices. This is almost the same as SO3. It's a rotation along the axis n by the angle theta, but in some spin space to the two component things. Actually, we can write this explicitly. It's cosine theta plus I n sigma sine theta. So how many different SU2 matrices do we have? N is a unit vector. It points in any direction. It's a two-dimensional point. I mean, it's a unit vector in 3 dimensions, which lives on the 2-dimensional sphere. And theta is a number. How many values this number takes? Theta can be 0, which means unit matrix. Yeah. Theta can be anything up to pi. So what's the difference? What's the difference between SO3 and SU2? The difference is the following. SU2 is also a solid ball. It's like a ball which is filled inside. We have unit vector n, direction, and angle theta, which goes from 0 to pi. But there is a very important distinction. Whenever you reach the surface of this ball, theta equals pi, what happens?
All the points become equivalent.
When theta equals pi, this thing is 0 and this thing is -1. All the points on the surface are equivalent and correspond to minus unit matrix. Minus unit matrix is also SU2. So all points on the surface are equivalent. Not just opposite, but all of them. And this space has a name. It's actually S3. It's a 3-dimensional sphere. It doesn't have a boundary. Yeah? If you go in any direction, you go in a loop, jumping. So it's a 3-dimensional sphere, and pi1 of SU2 actually is 0. It's trivial. All loops are contractible, even if it goes from one point on the surface to the opposite. Since the whole surface is the same point, you can continuously move this point to the origin and then contract it. So it's an important thing, because otherwise SO3 and SU2 are very much similar. They are very, very, very similar groups, but they have this slight difference. The same algebra, yeah. Okay, so I believe it's enough about homotopy groups. Yeah, actually the group pi1 is quite special. Pi1 is called a fundamental group. It has a special name. Fundamental group. And whenever it's not 0, whenever you have a non-trivial group pi1, you say that this particular manifold is not simply connected. Simply connected manifolds are those that have pi1 equal to 0. Simply connected exactly means that any loop can be contracted to a point. If it's not true for any loop, it's not simply connected. For example, if I have a board with a hole in it, it's not simply connected. And if there is no hole, it is simply connected. Okay, so why do we need this whole thing? Because we want to make some physical application. And this physical application will be the following. We will study homotopy groups of the sigma model manifolds. We have these 10 manifolds. We have homotopy groups of them. We can ask what these groups are. And there is a special table that is called, no matter, doesn't matter how it's called, so homotopy of sigma model manifolds. Sigma model manifolds. We will make a table. The first column will be the symmetry class. Then we will have, as usual, all our symmetries, t squared, ct, and c squared. In this order, it looks a bit nicer. Then we will have the manifold M. Q lives in the manifold M, so we will write what the manifold is. And then we will discuss what homotopy groups are. So, unitary class, the simplest one, A, unitary class A. No symmetries, 0, 0, 0. Q matrix lives in the space U2n divided by twice un. And then it's the nice thing about this table, then we go to another class which is A3, which is chiral unitary, and the only distinction is that it has this CT symmetry, but no other symmetries. And the manifold is just UN, it's just the unitary group itself. But I will write it now in a slightly different way. I will write it as UN times UN divided by UN. Yeah? So it's clear that you can cancel one UN. This is just a unitary group. Then I will go a little bit faster now, just to save some time. Orthogonal class. Class BD1, chiral orthogonal. Class D, superconducting unitary. Class D3, superconducting symplectic. Class A2, just usual symplectic. Class C2, chiral symplectic. Class C, another superconducting unitary, and class C1, superconducting orthogonal. 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. So, symmetries. Orthogonal class has T symmetry that squares to 1 and doesn't have any other symmetries. Class BD1 is chiral orthogonal. It has T that squares to 1, and it has C that squares to 1, and it has a CT symmetry as well. Class D, superconducting unitary, has C that squares to 1, but doesn't have time reversal symmetry. Class D3, superconducting symplectic. T squares to -1, C squares to +1, and there is a CT symmetry. Class A2, usual symplectic, -1, 0, 0. Class C2, chiral symplectic, -1, -1, and CT symmetry. Class C, another superconducting symplectic, another superconducting unitary, no, -1. It's like D, but with -1. Class C1, superconducting orthogonal, +1, -1, and density symmetry. This order, I ordered these classes in a very specific way just because it looks nice in this table. If you look, it goes like this snake. Another point, it groups 3 minus 1s in t squared and 3 plus 1s in ct squared here, or 3 minus 1. So it's like this snake, or you can view it in any other way. So now the spaces, the manifolds. For symplectic class, I remember it by heart. It's SP to 2n, let's make it 2n, by twice SPn. What about class BD1, chiral, orthogonal? It's U over SP, U n over SPn. Then class D, oh, that's easy. Should be easy, I believe. It's O 2n divided by un. D3 is even easier, it's just orthogonal, it's on. But, as I already did with class A3, I will do this trick. I will multiply on by itself and then divide it back, divided by on. Symplectic class A2, it's like this, but upside down. O to n divided by twice on. Yeah, we had this, I mean, unitary classes, u divided by twice u, orthogonal is sp divided by twice sp, and symplectic is o divided by twice o. C2, superconducting symplectic. Oh, it's u divided by o, it's un divided by on. Ah, no. Ah, yes, it's u divided by o, right. All chiral classes, A3, BD1, C2, they all have unitary divided by something. We also discussed this. It's unitary divided by symplectic, it's unitary divided by orthogonal. Class C, I forgot. What is missing here? I believe it's SP divided by U. And finally class C1, oh, that I remember, it's just a symplectic group. It's just SPn. Which, as I already did, I multiply by SPn, since it's a single group, and divide. So once again, we have these 8 classes in a particular order, such that we have this nice snake. And also, if you look at these spaces, they are also in a particular order, namely, whatever stays in the numerator in one line goes to the denominator in the next line. U was in the numerator, goes to denominator. Orthogonal was in the numerator, goes to the denominator. Double orthogonal was in the numerator, goes to the denominator. U in the numerator, U in the denominator. So, and it's a loop actually. This thing is cyclic. You can go after this back to the first one. And the same is true for these classes. And the A3, whatever is numerator goes to the denominator, but this is a loop of the length 2. Just goes back and forth. So why do we write it all this way? Yeah, the snake is also looped. And this one is also looped. It's not really a snake. It's, I don't know. So, homotopy groups, pi 1, pi 2, pi 3. I will not list any others. So what about class A, the unitary class? we have discussed there is a quantum Hall effect in the unitary class in 2 dimensions. We can have a Pruskian term or a theta term that takes the values from the that counts the degree of covering as S2 two-dimensional sphere, 2-dimensional real space into the manifold. Actually, it means that pi 2 equals z for this particular manifold. And this z is needed there in order to have quantum Hall effect. And yeah, actually, for all others, I just, of course, this is easy. I remember the answer. They go like this. And if you continue to higher dimensions, it always interchanges. 0 and z, they flip back and forth, back and forth. Now, about these 8 classes. This is a bit trickier. So class A1 orthogonal is the most boring one. It has 0, 0, 0. Nothing happens. Class BD1, chiral. Oh, that's easy, actually. Remember, we have these chiral classes, A3, BD1, C2. 3 chiral classes. What is special about them? They all allow this Gade term and this strange behavior of the density of states. This is all because they have a unitary matrix in the numerator. Unitary over symplectic, unitary over orthogonal. So they're the only classes where the Q matrix has a non-trivial determinant, which is a phase. This means that pi 1 fundamental group for all these classes, for all 3, actually is Z. This is BD1, and this is C2 somewhere, number 3 in this table. Why is it Z? You have a map. You map your whatever real space into your sigma model space, and then you take a determinant of it. So it's like mapping real space into a ring, one-dimensional sphere. So for pi 1, when you map from one-dimensional sphere to one-dimensional sphere, it's always Z. You can reduce any map to a map onto a simple circle by taking determinant.
We are divided by E of n. Also should can have from non-trivial space.
This one?
Not C.
Class C. No, it's only when U is in the numerator, not in the denominator. I mean, U has a determinant. If you divide U by orthogonal or symplectic, it still has a non-trivial determinant. Yeah, then what else do we have in this table? Actually, it's not so easy to explain why, but we also have in fundamental groups in pi 1, we have Z2 for class A2, for symplectic class, and for the class D3, which is just one line above, Z2. Then it is 0, and 0, and 0. And then the nice thing is that this periodic structure of our 8 classes, this cyclic structure and of manifolds, it leads to some periodicity in this picture here. So when we go to pi 2, we have 0, Z, 0, Z2, Z2, Z, 0. And here again 0, 0, Z, 0, Z2, Z2, Z. This is a mathematical statement, actually. There is a theorem that homotopy groups of these symmetric spaces, they're much easier than spheres, than what I discussed before, pi I of SD. These homotopy groups of these spaces are like this, and they have a pattern. When you change the dimension, they just go along the cycle, shifting by 1. Here it's the cycle of the length 2, here is the cycle of the length 8. this statement that homotopy groups behave in this way has a name. It's called Bott periodicity. Bott is a name, I mean, is a person. Bott periodicity. And once again, I already explained how in chiral classes we can have Z for the fundamental group. We have Z for the group pi2 in the unitary class, which corresponds to quantum Hall effect because we need this Prussian term in the sigma model to do it. And actually there are two other classes which are D and C, classes that in 2 dimension have this Z number. Classes A, C, D, all classes that have just a single letter in their name, are in some sense similar. They all have some versions of quantum Hall effect. I will show it later. And for example, there is another common statement about classes A3, D3, and C1. These are classes that live on the group where I can cancel one. So it's a unitary group, orthogonal group, and symplectic group. For these classes, actually, pi3 equals Z for all of them. And this is a known thing because these are the classes that allow to write a Versumina term in 2 dimensions. These are the classes where Versumina originally was found. I mean, in the original work by Vess and Zumina, it was just on the group. You have a matrix, Q, which belongs to a group. You write the action for this matrix, and then it turns out that you can add a special term to this action in 2 dimensions, which is called the Versumina term. So this was first discovered for pure groups, and only in 2 dimensions. What we had actually was a 1-dimensional Versumina term on the boundary of quantum Hall, so it corresponds to the same pi2 equals Z. But it's not the original Versumina term. So anyway, this is a table. We look at this table, we memorize it for a second, and we add a new page. So why do we need this table, which is just disappeared? Because this table tells us in which cases, in which dimension, and in which symmetry class we can actually add a topological term to the sigma model action. Because a topological term, like theta term, takes values, theta term in d dimensions, takes values, belongs to the group pi d of M of the sigma model manifold, literally. When you map, your Q matrix maps from real space to M. Whenever you have some topologically non-trivial maps, you can add a theta term to your action, which will take different values depending on which homotopy class your Q belongs to. And whenever you add a theta term to the sigma model action, you know that something happens to localization. So usually everything is localized. I mean, you add disorders, the system becomes less and less metallic, and eventually everything is localized. We have these beta functions that all on the left-hand side, no matter what dimension is on the left-hand side, they go into the insulator. So whenever you have a theta term in the action, something changes. Namely, there is a possibility that there will be no full localization. And actually it turns out that whenever this theta term appears, there is no localization. There is no full localization. And all these cases that were listed in the table are examples when, in which dimension, in which symmetry, we can have a state that is not fully localized. So, our next topic is called topological insulators. Topological insulators are special materials that are insulators they have everything localized, nothing moves, localized bulk inside the material, but delocalized surface. Delocalized surface. And there are examples that we already studied. Quantum Hall effect is such an example. Quantum Hall effect has localized bulk. Whenever we are in the quantum Hall plateau, everything is localized in the bulk, but there are edge modes that cannot be localized. So why do we have it? Because in class A we have pi 2 of m equals z, yeah, which allows us to add Pruiskian term to the action and show that it is not fully localized, at least at the edge. Another example that we had, yeah.
Maybe I missed something, but I thought quantum Hall effect is in conductors, not in insulators.
It's a formally insulator because everything is localized in the bulk.
But I thought to take a two-dimensional conductor.
You take a two-dimensional metal, add magnetic field,
So
cool it to very low temperatures, and everything is localized. Current flows only at the edge. Current doesn't flow inside.
So quantum Hall effect is about insulator.
It's a topological insulator. It's an insulator which has conducting edges. So
But also inside there is some current.
no, if you are in the one of quantum Hall plateaus, there is no current inside.
Okay.
And if you don't have magnetic field, you can localize everything, so there will be no current neither inside nor outside, it will be just insulator. So the other example that we studied is called quantum spin Hall effect. It's very similar, it's class A2 symplectic, and it can either have a pair of edge modes that is not localized or don't. There are only two possibilities. And to distinguish between these two possibilities, we added a theta term, a very specific Z2 theta term, but to the edge theory, not to the bulk, to the edge. And this is possible because pi 1 of m equals Z2. Pi 1, so it's a two-dimensional object, but we look only at the edge theory, so that's why we need pi 1. And now anybody who has still access to that table, I don't have it here, can you tell me in class A2, is it true that pi 1 is Z2? Right? Okay, very good. So we can generalize these two cases to any class and to any dimension, and this is the statement. There are two types of topological insulators, Z-type and Z2 type. Z means you can have any number of delocalized surface modes, and Z2 means you either have 1 or 0. So Z topological insulators, Z topological insulators exist. Let me put it, that looks a bit scary. D-dimensional Z topological insulator is possible only if pi d of m equals z. So whenever you are in the dimension d and in that table you see the letter z, it means that in that class you can create a topologically insulating state. And in d dimension, a Z2 topological insulator is possible and does exist only when pi of d minus 1 of m equals Z2. Because for Z2 we don't have this Versumina physics, so we need a theta term on the edge, not on the bulk, but only on the edge, like we had here. So these are the two examples of these two general statements. So for Z topological insulators we need pi d to be z. For Z2 we need pi in the dimension 1 less to be Z2. And I will go back. Is it back? Yeah, to the table. So this Z here, pi 2 in class A equals Z, this is quantum Hall effect. Quantum Hall effect is possible due to this Z here. What else is possible? There are other Z's in 2 dimensions, and this one here, this is class D, right? It's called, we will not discuss it, but it has a name. It's a thermal quantum Hall effect, thermal quantum Hall effect, and this one is a spin quantum Hall effect, SQHE. This is spin, S stands for spin, and T stands for thermal. And they both happen in some superconducting classes, so it's quite strange objects. It's like spin quantum Hall effect. It's like when you apply voltage, there is a perpendicular spin current, not electrical current, but spin current. And this one is when you apply voltage and there is a perpendicular thermal current, not charge and not spin, just energy current, just heat current. So you can have quantized Hall effect with these currents in these 2 classes because we have Z in these entries here.
How can I understand it from entries?
There are H states that propagate spin or energy but do not propagate charge.
It's obvious that from this symmetry there is thermal quantum Hall effect, right?
What is obvious?
No, it's like, for example, in that Z, for this Z corresponds thermal quantum Hall effect.
Oh, that's just because because they're superconducting, they cannot produce usual quantum Hall effect, because in superconductors you cannot apply electric field to a superconductor properly. Any current will be shunt by the superconducting bulk. That's why you either have to study spin current or thermal current. And here you can have spin current, and here you cannot, because you also break spin symmetry. So actually this 1 and minus 1 corresponds to CT, which with strong spin orbit coupling and without strong spin orbit coupling breaks spin symmetry, so there is no spin symmetry in class D3. That's why it's thermal, in class D. That's why it's thermal, and there is spin symmetries in class C, so you can have a spin current. But again, this is not the topic that I wanted to discuss, it's just to mention. Then there are 3 Z's in 1 dimension, A3, BD1, C2. Chiral unitary, chiral orthogonal, chiral symplectic. We discussed this. This Z is responsible for Gade and Wegener theorem. It's responsible for the absence of perturbative corrections to sigma. This also means that you can have a topological insulator in 1 dimension. What is it, 1-dimensional insulator? It means there is a gap in the bulk, or everything is localized in the bulk, and then there are some H states at the end of this 1-dimensional line, and it can be any integer number of these H states. So this is actually called the Suschrieffer-Hager model, with this 1-dimensional with the states, or polyacetylene model for some 1-channel case. We also did not touch this, but I just wanted to point out that they're also in this table. And finally, there is a very famous thing which is called Majorana fermions. In a very similar situation, 1-dimensional wire with a Majorana fermion at the edge, for example, it's called Kitaev model in some cases, but we don't have them in this table. Why? Who can tell me why we don't have them in this table? This is a tricky question. No, this is the wrong answer. Other?
Is it a point that this D should be video or something, that there is some constraint on disorder or something?
No. The reason is very simple. Majorana fermions, you can have only either one or no of them. If you have 2 Majorana fermions, they form a usual fermion and disappear. So they are Z2 1-dimensional topological insulators. And to have a Z2 one-dimensional topological insulator, you need pi 0 to be equal to Z2, and we don't have pi 0 in this table, that's why. But if we move one column to the left, these Z2s, they will shift one line up. So Majorana fermions exist at the edge in classes D and D3. Actually. And Kitaev model is class D, I believe. Yeah. One-dimensional model of class D with some strange topology. So I also mentioned this Z in 3 dimensions. They happen on the group manifolds A3, D3, C1, and they correspond to Vez-Zumina term, which means that in principle you can have something like what? Like a 3-dimensional topological insulator. So you have a surface which hosts. It's a pi 3. It's like quantum hole, but in 3 dimensions, right? Z. Yeah, you can have this Vez-Zumina theory in 2 dimensions, which is like a surface of a 3-dimensional Z topological insulator. I'm not aware of any good realizations, but what I am aware of is this thing. Pi 2 equals Z2 in class A2. This is the most interesting. Well, not the most, they're all interesting. This is an interesting entry in this table, which tells us that in class A2, in symplectic class, we can have Z2 topological insulators, not only in 2 dimensions. This is, by the way, quantum spin Hall effect that we discussed some lectures ago. Please, this is very important. Nobody actually pays attention. Quantum spin Hall effect is not the same as spin quantum Hall effect. They are in different dimensions. Well, they are both 2-dimensional, but one is in symplectic class, the other one in class C. This is very important. These are 2 different effects. So we also have Z2 here in pi 2, symplectic class, which means we can have a 3-dimensional Z2 topological insulator. And on the surface, we will have something delocalized. On a 2-dimensional surface, we will have something that cannot be localized. Sorry, let me finish, please. And this case is very well studied. It has experimental realization. It's what people usually call topological insulator. The term topological insulator was more or less invented first to describe this case. It's a 3-dimensional system with time reversal symmetry of symplectic class with interesting surface states, and the rest of this lecture will be actually devoted to this case. Yeah.
In terms of experimental realization, what is the difference between quantum spin Hall effect and spin quantum?
This is a quantum spin Hall effect, 2-dimensional system with strong spin-orbit coupling such that you have counter-propagating spin-polarized modes at the edge. Spin quantum Hall effect is a 2-dimensional system where you have only chiral modes propagating in one direction, but conserving spin, but not conserving charge. So it's a superconducting system. It's a very different object. This one, quantum spin Hall effect, is experimentally realized in quantum wells in mercury telluride mostly. This one is never experimentally realized. Nobody knows. But it's a fascinating theoretical thing. I mean, there is some very deep theory that allows you to calculate all the critical exponents analytically. This is a very rare case in here. So it's very much studied theoretically, but there is no experimental realization. That one is mercury telluride quantum wells without superconductivity. Okay, any further questions to this table or just questions?
So before you promised us there will be applications of P groups.
This is the application. I already showed you.
Okay.
This look, it's P, and this is all physical applications. So knowing these groups tells us where should we expect topologically non-trivial metals that cannot be fully localized. And we have physical examples for most of these cells that whenever we do have something, indeed there is a special material that due to topological reasons cannot be fully localized, where metal where electrons cannot be fully localized. So let me move on. So it is this case, Z2 topological insulator in d dimensions is possible when pi of d minus 1 of m is Z2. So pi 2 of the manifold of symplectic class, which is O divided by twice O, is actually Z2, and this allows us to have, let's say, ordinary topological insulators. Ordinary topological insulators. So it will be very fast. I mean, now this will be something physical with simple equations, no topology, nothing. Very simple stuff. I learned to add a new page each time because otherwise I cannot scroll this thing. So, ordinary topological insulators. Ordinary topological insulators. Three-dimensional system. T invariance, but spin is broken, so strong spin-orbit coupling. Strong spin-orbit coupling. And it should be actually so strong that you have a gap in the spectrum. So to make it an insulating, you can open a gap. And there is a prototypical Hamiltonian how to describe a three-dimensional system with a gap, strong spin-orbit coupling, with highest possible symmetry. And the answer was actually derived about 100 years ago, before any of this stuff even happened, and it's called Dirac-Hamiltonian. Dirac-Hamiltonian is the Hamiltonian which describes relativistic electrons, just usual relativistic electrons in vacuum, and it looks like this. There are many ways to write it, but I prefer this way. Minus m plus m sigma dot p. It's a 4x4 matrix. It's a famous thing. Everybody learns it now in kindergarten. It's a 4x4 matrix, which is linear in momentum. Sometimes the coefficients are called gamma matrices. And it has a spectrum. Energy is plus or minus square root of m squared plus p squared. If you just diagonalize this matrix. And actually each branch of the spectrum is twice degenerate, is doubly degenerate, and this is called spin. Electrons have spin. For a given momentum and given energy, there are two states with spin up and spin down. So the spectrum is, everybody knows, P, energy. This is like an imaginary straight line, and then this is the spectrum. There is a positive branch and negative, and the gap is m, plus m and minus m. And when Dirac first proposed this Hamiltonian and found this spectrum, he said, wow, I have too many states here, not only positive energy, but also negative energy. So what should I do? I should propose that they are all filled. All the states here are occupied. They're fermions, they're occupied. But if you remove one fermion from here, you have a hole. This is what will be called positron. So this is just the basic thing for relativistic quantum mechanics. Now, we will take the same Hamiltonian, exactly this one. It's three-dimensional. Momentum is three-dimensional vector. And we will say it does not describe electrons and positrons. It describes some material with a spec which has electrons inside. And in the spectrum of this material, we somewhere have a valence band, which is filled, a conduction band, which is empty. They come close at a certain point in momentum space. And we can approximately write the Hamiltonian as an expansion near this point. And this expansion starts with zero order, with a constant, plus linear term, plus quadratic. And so we just take linear terms into account. So we have some zero order term and some linear terms. And then we can choose the basis such that it looks like these gamma matrices. Not always, but if we also have time reversal symmetry, for example, we can do this. So this is like a prototypical Hamiltonian to describe any small gap in the spectrum of a semiconductor with strong spin orbit coupling. And we can actually prove that this type of material, it has a gap. It's not a metal, it's an insulator. This is filled. This is empty. Chemical potential is somewhere in between. There is no Fermi surface. Chemical potential doesn't cross the spectrum. It's an insulator, but it can have states on the surface. And we will right now derive the surface Hamiltonian. From the bulk Hamiltonian, we can derive the surface Hamiltonian. This is a very nice, from my point of view, very nice exercise. So, surface states. Imagine we have a state. It's a three-dimensional thing. Imagine we have a state with energy zero, right in the middle of the gap. I would like to find a state with energy right in the middle of the gap. I know such states do not exist because it's a gap. Yeah, there are no states. However, I still can invent a function. Let me call it psi, with capital psi. It's my wave function. And I will say, I want a function that behaves like this, m times x. It's an exponential, but it's not an imaginary, it's a real exponent. So it exponentially grows in positive x and exponentially decays in negative x. It cannot be a real eigenstate because it's not normalizable. Right? Exponentially grows. But it can have zero eigenvalue. And it will have zero eigenvalue. So there is some spinor here, psi and chi. This is a small psi, this is a capital psi. This is just some constants. So I want to select these constants such that this whole thing is the eigenvalue, is the eigenstate of this Hamiltonian. Let's try. We act with the first row in this column, and we get minus m times psi from here, and sigma p acting here, actually p is the derivative, it's px, py, pz, there are derivatives, so we can take derivative in x acting on this exponent, so it will be minus I m sigma x times chi. Minus I m is the result of acting by px, then I multiply by sigma x, and this matrix acts on chi because this is the first row times this column. And this thing I want it to be zero. I just want to find a state with zero eigenvalue. And actually m cancels from here. And I see that there is a relation between psi and chi. And if this relation is fulfilled, my state is the eigenstate. So the relation is chi equals I times sigma x times psi. So if I have this state and psi and chi are related like this, it's the eigenstate of this Hamiltonian. You can check the second line will also give zero. It's easy. So this is the eigenstate of this Hamiltonian with eigenvalue 0, and it's not normalizable because it has this exponent inside. But if I have my sample which for some reason occupies only half space. This is x direction, and my material occupies half space for negative x, and there is nothing for positive x. I have a surface. This is the surface. I still can imagine that these states exist somewhere near this surface. So it decays exponentially into the bulk, but it does not exist on the right. That's why it is still normalizable. I don't need to integrate the divergent integral. So this state decays in the bulk, and then it's just 0 on the other side. And in order for such state to exist, I need to impose a certain boundary conditions on this surface. And the boundary conditions are exactly like this: chi equals I sigma x psi. So if I have a Dirac Hamiltonian here with this boundary condition, I will generate a zero energy state inside the gap, which lives near the surface. And actually I can generalize this condition, by writing chi equals I sigma n psi. So now I have a sample which is not a half space, it's just some random shape. And at each point I define n vector, which is the normal vector to the surface. And then near this point, with this normal vector, I say this is my boundary condition. It's just generalization. Sigma x corresponds to the normal vector pointing along x. Yeah, now if I rotate it, if I rotate my sample, this sigma will rotate as well. The Hamiltonian is fully rotationally symmetric. I mean, this sigma dot p, you can choose any basis. So this is the boundary condition that I should supply to this Hamiltonian in order to have surface states in it. And I can now derive it. So with this boundary condition, this state has exactly zero energy, and it's right in the middle of the gap. Now imagine my solution will not be this. I will do some small variations. I will allow it to travel along the surface. So to have some y and z dependence. And here it's only the function of x. If it also depends on y or z, it can have a momentum in this direction. It can propagate. Then probably energy will not be exactly zero. So let's see. Now I slightly change my notations. This is important. New notations are like this. Wave function psi equals small psi here and small chi here, I sigma n psi. But I removed this exponential. I don't like it. I removed it. If you like it, it is now part of this function. I have hidden it inside this function. So this is my, very generally, this is my wave function that obeys the boundary conditions. And I will act with the Hamiltonian on this function, and I will see what happens. So the first row of the Hamiltonian acts like this: minus m times psi plus sigma p, this is scalar product of sigma and p, times I sigma n psi, right? This is, I acted with the first row on this column. If I act with the second row, I will have sigma p times psi plus m times I sigma n times psi. And in the first row, I should get energy times psi, and in the second row, I should get energy times I sigma n psi. So what should I do? In these equations, I have a large number. M, the gap, is the large parameter. I want my states to live very deep inside the gap with energies much smaller. Energy is much smaller than M. And to do this, I will say that I have this big number here and this big number here. I want to get rid of them. I want my Hamiltonian, my effective Hamiltonian, to resolve small energies, and it has these big constants. I don't like them. So how do I do this? I take my second equation and I multiply it with minus I sigma n. And then I add first equation to the second one, which with this factor. When I do this, I will cancel these two terms, because sigma n squared is just 1, minus I times I is 1, and minus m plus m is 0. And also, just look what happens. So if I do it like this term will cancel against this term, and these two remain, and I can write them like this. I times this one, sigma p sigma n times psi, and this one is minus I sigma n sigma p, minus I sigma n sigma p. This whole thing times psi equals, and on the right hand side I have energy, and from here I have another energy. It's just the same. So I have twice energy times psi. Now I have an equation which involves only two components, not all four components, but only a two component part of the original field, because actually boundary conditions fix 2 out of 4 components, so there are only 2 remaining. And it's a linear equation which does not contain any large parameter m. It only lives at low energies. So there is an effective surface Hamiltonian, which looks like this. It's I divided by 2 commutator of sigma dot p with sigma dot n. That's it. This is the surface Hamiltonian. Right. This is what I wanted to derive. And this is a very nice object because, look, P is a vector, is a real vector. It rotates, when you rotate your, what's the name for this? Reference frame, the components of P change as the components of a vector. N is also a real and true vector. That's nice. Sigma dot P is a pseudo-scalar. It is like a scalar, but it changes sign if you do inversion. Sigma n is also a pseudo-scalar, and the commutator of them is a real scalar. So Hamiltonian is a real scalar. It does not depend on how you choose the basis. Wait a moment. And also, it's an explicitly Hermitian operator. Yeah, it's a commutator of two Hermitian operators, which is anti-Hermitian. With I, it's explicitly Hermitian. Yeah.
Do we need to add a condition which comes from that at the zero order m should cancel? So it's like you can say that energy is literally zero.
I didn't really get your question, but yeah, we had a solution that is exact for zero energy, and then we a little bit, if you like, deviate from this solution, and energy deviates from zero.
And do we have any condition that actually we are on the surface, but just slightly deviates?
Sorry, it slightly deviates from the surface. I did not understand. We are on the surface. our state actually decays in the bulk exponentially. And this is, M is a large parameter, so it decays very fast. It's really, really two-dimensional.
I mean, in the beginning we had two equations, and now we have just one. So we should somehow satisfy the second one.
Well, I satisfied both of them. Well, I formed a linear combination which doesn't contain M. You can form a different linear combination which will contain M, which is a big number, and this other equation will just tell you how your state decays in the bulk. It will know nothing about motion along the surface. It will be just an equation that provides you this exponential factor. So I specifically took a combination where M cancels such that I can, on top of this large thing, so I have large M, which cancels large p times this exponential. There are two large terms in the Schrödinger in the Dirac equation that cancel out, and I concentrate on the other terms that are small, that live on the background of these large terms. And for them, I have this thing here. So just to make you, to give you some feeling about this Hamiltonian, it looks quite nice to my view, and also there are some simple limiting cases. For example, imagine we have a surface that is flat with a vector n, with a normal vector n, which is a constant. It's just a constant. Yeah, let me point out this. So if n is a constant, there is only one sigma matrix here, no n. And since it's a commutator, it means that here only two other sigma matrices can appear, because sigma matrix commutes with itself, so we need two others. Which means that only the components of momentum that are orthogonal to n actually appear in this Hamiltonian. That's why it's a surface Hamiltonian. There is no components of momentum transverse the surface. And for example, if n is, let's say this is a z direction, n equals z. It's not that z, which is integer number group, it's just unit vector along z. The Hamiltonian will be what? I over 2 commutator sigma x px plus sigma y py commutator with sigma z. And I don't add here sigma z pz because they do commute and it will be 0. So if anybody remembers commutators of sigma matrices, x with z is minus 2iy, so it's px sigma y minus py sigma x. This is the result. And this is actually a two-dimensional Hamiltonian, linear in momentum, which is sometimes also called the Dirac Hamiltonian, which is the same as in graphene, for example. When you have a spectrum, the spectrum looks like this. It's just a cone goes through 0. It's two-dimensional. Energy equals plus or minus absolute value of p, of two-dimensional p. So in fact, we have this spectrum of Dirac Hamiltonian, which has a gap, and then this cone is inside this gap. It's like fit in the middle of this gap. And it describes only the surface states, that gap above and below. That gapped part is the bulk states that propagate in the bulk. And they have some large energy. And for low energies, we have only this cone here. So this is one case. And you can also do the same trick. You can take any curved surface and will be a function of position. And you can just compute this commutator and see what the Hamiltonian is. And this will be a homework. for the next lecture in a few years. Homework. Consider a cylinder. Cylinder is a simple thing, right? Cylinder of radius r, of radius r. It's like this. You have a cylinder. There is a radius r, and it's infinite in z direction. And this cylinder is actually made out of this topological insulator. So there are states on the surface, but no states in the bulk. So the question, the homework, the task is to take this Hamiltonian and to write it in cylindrical coordinates and to see what are the eigenstates on the surface. And since this next lecture, I'm not sure when it can happen, so I will give you immediately the correct answer. I mean, I will not write the Hamiltonian, I will just tell you what the energy is, what are the eigenvalues of this Hamiltonian. The eigenvalues are plus and minus square root, as usual, pz squared, momentum along the axis of the cylinder, plus 1 over r squared times n plus 1/2 squared, where n is any integer number. So n is like quantized momentum along the cylinder, pz is the unquantized, the continuous momentum in the z direction, and the nice thing is this 1/2, because if you have just the usual metal, like aluminum foil, you make a cylinder, you say there is a quantization around, you compute, you will have exactly the same thing without 1/2. So this 1/2 happens because you have strong spin-orbit coupling, your spin is bound to momentum, and when momentum goes around the circle, spin should also rotate, and when spin rotates once, it changes the sign of the wave function, so the boundary conditions have an extra minus sign, so you have a different type of quantization.
Like Landau levels in magnetic.
Landau levels in magnetic field also have 1/2 in that point, but I wouldn't say it's due to some spin rotation, because there's no spin. With spin, actually, they do not. Okay, so why do we need this strange object? We need this strange object on a cylinder because I would like to prove to you that these states on the surface indeed cannot be localized by disorder. And in order to prove this, I will, to this model, I will add something strange. First of all, I will make another hole in this cylinder, so it will be now a tube. A tube which has outer surface and inner surface. And this tube, which has two surfaces, on each surface, bless you, on each surface there is this type of spectrum. And on top of this, I will add magnetic flux going through the tube. Magnetic flux of a very specific value. Magnetic flux phi, which equals hc over 2e, or in other units, pi h bar c over e. This is called half flux quantum. It's the flux that you usually have inside the superconducting vortex, this value, half of a quantum. This flux is nice, this particular value is nice because it introduces exactly the same boundary conditions. When you go once around, your wave function must change sign because it accumulates the phase, which is exactly half of 2 pi. accumulates the phase pi. So with this magnetic flux, the spectrum changes, and now it's plus and minus square root of pz squared just plus n squared over r squared. There is no 1/2. There is no 1/2. And this magnetic flux actually does not violate time reversal symmetry when it has this half integer value. Any other value violates time reversal symmetry. This one doesn't because, as I said, it only means that you have a new boundary condition. When you go around this flux, you should flip the sign of the wave function. But if your wave function is real, you flip the sign, it remains real. So you do not introduce any complex. So violation of time reversal symmetry usually means that you don't have real solutions anymore. You have only complex solutions. So time reversal is preserved, but boundary conditions changed. Time reversal preserved. And the final touch, you have a one-dimensional system. Now it's one-dimensional only in z direction. You have some continuous momentum in the transverse directions. Everything is quantized. It's a one-dimensional system. And we can draw a spectrum of this one-dimensional system, pz, this function, this one. So for n equals 0, we have a very specific thing which is a straight line. Yeah, E equals either plus p or minus p. And for all other values of n which are not 0, we have some curves like this or like this. This is n equals 0, 1, 2, this is 0, 1, 2. This is energy. Now, question. Imagine I fix some chemical potential in my system. I fill all these states on the surface. It's now a two-dimensional metal. The bulk is gapped, insulating. It's not interesting. It's only a two-dimensional surface. It has these eigenstates on the surface, and I fill them up to this chemical potential, which is still inside the gap for the bulk. How many channels this one-dimensional system has? Conducting channels.
Two in this picture?
Sorry?
Two in this picture?
Two? No, that's wrong.
Maybe four.
4 is also wrong. Other options? Whoever gives the correct answer is relieved from the homework. The correct answer is 3. Let's count. This is 1. This is 2, right? And there is also n equals minus 1, which is also here. N is an integer number. And I showed you only the positive numbers here, but they're also negative. So each curved line here is doubly degenerate. And only this straight line without a gap is not degenerate. It corresponds to n equals 0. So actually it's plus minus 1 and plus minus 2, and each of these lines are twice degenerate, and the gapless line is not degenerate. So actually, no matter at what level you put your chemical potential, here or here or here or here, the number of channels is always an odd number. Because you start with 1, and then you add 2 plus 2 plus 2 plus 2. It's a one-dimensional system along the cylinder with an odd number of channels with strong spin-orbit coupling. We studied this case before. In the previous lecture, it was the edge mode of the quantum spin Hall effect. Now it's not a quantum spin Hall effect. It's a surface mode of 3D insulator, which we compactified and made one-dimensional. And we know that in this one dimension, it cannot be fully localized. So there will be one channel. Since the number is odd, we already know that they will not be fully localized. So it's odd number of channels which means no full localization. So some channels can be localized, but not all of them. And since, and this actually proves from this statement, we can conclude that there is also no 2D localization on the surface. Why? So there was a two-dimensional surface. We made a cylinder out of a two-dimensional surface. If this two-dimensional surface was fully localized, it would have some localization length. So each wave function, each electron will live only on some finite. We can make a cylinder which is much larger than this localization length, much larger. And these electrons will never even learn that they live on the cylinder because they are localized on a scale where they don't see the boundary condition, the periodicity. So if everything is localized in 2 dimensions, it means that also everything should be localized in 1 dimension in this cylinder. And vice versa, if not everything is localized in 1 dimension, it means not everything can be localized in 2 dimensions.
Why does the odd number of channels imply no full localization? Is it because channels would scatter in pairs, or?
Yeah, actually, this is the case that we discussed maybe 2 lectures ago. It was called quantum spin Hall effect. It was a theory with the edge, which is spin polarized and counter-propagating, and there we derived a sigma model with a Z2 theta term, and this theta term is present only when the number of channels is odd, and not present when it is even. So in a sense, they will be all localized except for this single channel, which has no gap. Which is, if you like, if you go with the chemical potentials here below all these other things, then there is only forward scattering. If you have spin up propagating one direction, spin down propagating in the opposite direction, and potential impurities cannot flip the spin, so there is no backscattering. So if there is only one channel, it's just fully delocalized. If there are many, but the number is odd, they will be all localized except for a single one. So that's kind of a proof that this 2-dimensional metal on the surface of a 3D topological insulator cannot be fully localized by disorder, which is consistent with the fact that we had Z2 in the specific entry in that table, and actually for any other entry we can also build some Hamiltonian and proof. This proof, by the way, I didn't tell you, this proof is very similar to what is called the Laughlin argument, how Laughlin proved that in usual quantum Hall effect there are delocalized states. He also made a cylinder, had a magnetic flux, but there the magnetic flux was not half a quantum, it was a parameter that was changing, and by changing it by 1 quantum you can count how many. Okay, unfortunately I didn't present this argument in my lectures, but it's a very famous thing, like you can read about it in many places, and this one is its version for quantum spin Hall effect, I mean, not quantum Hall effect, which is written in much fewer places. So that's all. I'm very grateful to all of you for your patience for all these 9 lectures. Now everything is finished and you can ask questions about anything, including what was in the first lecture. Thank you.